The null space of a matrix, designated capital N of A, in the case of matrix A, is your set of solutions of the vector equation AX equals 0. A times the X vector equals 0, where A again is your matrix. Present matrix is 2, 4, 8, 1, 1, 7, 1, 3, 1. The equation AX equals 0 then is this matrix multiplied by, I'm going to use x1, x2, x3 for the three components of my x vector, and of course 0, 0, 0 for the components of my 0 vector. Okay, well, this is a matrix equation. Looks like you ought to be able to invert the matrix and get the solution x1, x2, x3 equals the inverse matrix multiplied by 0, 0, 0. And if that's the case, of course, then any matrix that's multiplied by the 0 matrix is going to give you the 0 matrix, which means x1, x2, x3 would be the 0 vector. Your null space would simply consist of the 0 vector. Now, the fly in the ointment here, so to speak, is that turns out this vector is not this matrix is not invertible. We can check its determinant. Its determinant is 0. It doesn't have an inverse. And of course, if you recall, when we reduced this matrix, we got a row of zeros, didn't we? That tells us for sure that the determinant is 0. And that row of zeros made the dimension of the row space less than the dimension of the matrix, which is 3 by 3 matrix. We're in R3. We only had 2 independent vectors in the row space. It's going to turn out that that means that we have to have one vector, or at least a one-dimensional null space. And we'll see that we do. Okay, so determinant of A is 0. There's no inverse, so we can't solve this matrix equation by using the inverse matrix. We have to solve it by reducing the matrix. Well, the matrix reduces down. Well, the 3 by 3 matrix reduces the same as it always did. And there's nothing we can do as far as adding rows and columns and multiplying by rows. Adding rows and multiplying rows by the same number and adding multiples of rows and interchanging rows. None of that is going to affect this column. This column, we're just going to be multiplying zeros. We're going to be adding zeros. We're going to be interchanging zeros. So we're going to end up with just zeros over here, which leads us to the equation x1 plus 10x3 equals 0, x2 minus 3x3 equals 0. How do we solve that? We only have these two equations. What are possible solutions? We could let x3 equal 1. Okay, if x3 equals 1, that means x1 is negative 10 and x2 is plus 3. So we would have a 1 for x3. x1 would be negative 10, x2 would be 3. We'd have the vector negative 10, 3, 1. Okay? Now that's the only one I saw when I asked people to tell me what the vectors would be if you have this solution. And everybody pretty much saw that. They pretty much said, okay, well, let x3 equal 1 and see what x1 and x2 are, and there's our vector. So people did quite well with that. Okay, but also we could have let x1 equal 1. If x1 is 1, then x3 has to be what? Well, 1 equals 10x3, negative 10x3, so x3 is negative 1/10. So if x1 is 1, x3 is negative 1/10, and if x3 is negative 1/10, then x2, if we substitute negative 1/10 for x3, x2 is going to equal 3/10, negative 3/10. So you can verify that. Also, if we let x2 equal 1, we get these components. Even more generally, we could let x3 be t, so that x2 is 3t and x1 is negative 10t, and you can verify that that would be the solution, so that your general vector might be negative 10, 3, 1 times t, where t could be any real number. Well, it then follows, and you can think about exactly why it follows, and you should think about exactly why it follows, that your null space is the span of this vector, negative 10, 3, 1. Okay? Or you could write it as the span of 1, negative 3/10, negative 1/10. This is in the span of this vector. and so is this one. You could use any vector. You could take any number t and multiply it by negative 10, 3, 1 and get a vector whose span is your null space. So you want to think about that. Now there's a great big deal involved here, and the big deal is that for square matrices, the dimension of the row space plus the dimension of the null space, or what I call the nullity, is equal to the dimension of the whole blame space. Now this also can be extended to matrices that aren't square, but once we see this, it opens the door to understanding everything else. Okay, and what did we find? The dimension of the row space of our matrix was 2. We reduced the matrix. We found that the row space could be spanned by 2 linearly independent vectors. So the dimension of the row space was 2. The null space can be spanned by just this one vector, or this vector, or this vector, or in general, this vector. Okay? It's the span of, and we chose to write it as the span of this vector. Single vector is obviously linearly independent of itself. So the dimension of the null space, or the nullity, I should say the dimension of the null space, the nullity is the dimension of the null space, so I didn't really write that quite right, is 1. Well, dimension of the row space is 2, dimension of the null space is 1. The whole space has dimension 3, because your vectors all have 3 components. So the dimension of the whole blame space, dimension of the row space, plus the dimension of the null space.